Hello, this is a physics project under the supervision of Dr. Mustafa Amin and STEM Ismailia High School. My name is Mariam and we're going to explain. My name is Mariam Abdurraouf and we're going to explain the second law of thermodynamics. Here we have Kelvin-Planck form of the second law of thermodynamics. Simply, the law states that it's impossible to construct a heat engine that, operating in a cycle, produces no effect other than the input of energy by heat from a reservoir and the performance of an equal amount of work. It simply states that it's impossible to construct a heat engine that produces no effect other than the input energy and the performance of an equal amount of work. This statement simply of the second law of thermodynamics means that during the operation of a heat engine, WENG, or the total work of a heat engine, never be equal to the absolute QH. Here absolute QH, we know that it is the amount of energy that leaves the heat engine, or alternatively that some energy absolute QC, the amount of energy that leaves the heat engine, must be rejected to the environment. We're going to explain heat pumps and refrigerators, which are devices that reverse the natural direction of heat and of energy transfer. In a heat engine, the direction of energy transfer is from hot reservoir to cold reservoir. We have here, which is the natural direction of energy transfer. We have here heat pumps. Heat pumps and refrigerators are devices that opposes this natural direction and transfers energy from the cold reservoir to the hot reservoir. Example, homes in summer are cooled using heat pumps called air conditioners. The air conditioner transfers energy from the cool room in the home to the warm air outside. This cools the home. In a refrigerator or a heat pump, the engine takes in energy. This is unlike the heat engine. The heat engine, the absolute QC, is the energy that leaves the engine, and the absolute QH is the energy that enters the engine. Here we have the opposite. In a refrigerator or a heat pump, the energy that enters the device or that enters the heat pump is absolute QC, and the energy that gets expelled from the refrigerator or a heat pump is absolute QH. Second law of thermodynamics, Clausius statement or Clausius statement. It simply states that it's impossible to construct a clinical machine whose sole effect is to transfer energy continuously by heat from one object to another object at higher temperature without the input of energy by work. In simpler terms, energy does not transfer spontaneously by heat from a cold object to a hot object. Work input is required to run a refrigerator. Here we don't have a spontaneous energy transfer from cold objects to hot objects, but this it officially needs work, or it definitely needs work input required to transfer energy from cold objects to hot objects, which is the opposite of the natural direction of energy transfer. Here we have the coefficient of performance. The coefficient of performance is simply the effectiveness of a heat pump. It's described in terms of a number called the coefficient of performance. Coefficient of performance, or COP, cooling mode, equals energy transfers at a low temperature, absolute QC, over W, work done on a heat pump. A good refrigerator should have a COP typically 5 or 6. We have another law for the COP for the heating mode. The heating mode is energy transferred at a high temperature, QH, over work done on a heat pump. So pause the video and try to solve the problem with the previous law, and here's the solution. We have the power equal work over delta T, and delta T, which is the time, equal work over power. Delta T equal QC, then equal QC over COP, or over power times COP. Delta T equal mass times delta T plus LF times delta mass, or the average mass, over PC times COP. This gives us, we have to take the mass in common, and if we take the mass in common, mathematically it will be delta T equal absolute mass times delta T minus LF over B times COP. This, if we substitute by the values of each variable here, we will get that delta T, the time taken for this, is 83.3 seconds.